Okay, let's continue. So in the first two parts, we focused on some sort of technical ideas, and the main problem that we are facing is that we are now dealing with quantum many-body problems, where we are working in this huge many-body Hilbert space, and what I discussed is some way out. I mean, like some ideas how we can efficiently simulate these systems by basically focusing on a tiny part of the Hilbert space. And then it allowed us to come up with some algorithms, which was this TEBD and the DMRG algorithms that allow us, for a given Hamiltonian, to find ground state representations of those. Good. So this gives us some sort of technical tools to study systems. But ultimately, we are interested in understanding topological phases. And this is what I want to talk about in this kind of second part. Of course, there's lots to say about this, because in the presence of interactions, we have like a large zoo of different topological phases that can emerge. And I just want to give you a glimpse at this and discuss in some more details so-called symmetry-protected topological phases. And these are, in a way, generalizations of topological insulators, right? Like a topological insulator, like a Z2 kind of topological insulator, is a symmetry-protected topological phase, in that case, for example, by time reversal symmetry. And here I want to discuss the generalization of these concepts to genuine interacting models. And the, I think, neat connection to what we discussed before is that those topological invariants, they can be just basically read off from the matrix product state representation. Right? So what I want to do now is I want to give you a kind of quick kind of crash course to these kind of symmetry-protected topological phases, and then show, going back to this matrix product state representation, and show how we can extract this topological invariant directly from these DMRG type simulations. So let me, for concreteness, start by looking at a concrete model. And this is a spin 1 Heisenberg chain. So it's a simple Heisenberg model, like this isotropic Heisenberg interactions between neighboring spins on a one-dimensional chain. And each of these sites is a spin 1 degree of freedom. So a while ago, like in the early 80s, that Haldane argued or conjectured that the ground state of this Hamiltonian is gapped, right? And it does not break any symmetry. Which means that if we put the system on a ring as such here, and we would diagonalize this Hamiltonian, we would find that there's a unique ground state, and then there's some energy gap to some excitation continuum. The reason that this was quite exciting and potentially also unexpected is that for half integer, like for the spin 1/2 chain, there's an argument based on Liebschultz matrix that the ground state is actually gapless. And at that point, people knew for half integer spains that the system is actually either gapless or it has to break the symmetry. Not much was known about integer spin chains. And then it came as a surprise that those systems are actually gapped. Good. But it turns out, like at this level, it just looks as if it were just a simple paramagnetic ground state. But there's some sort of a surprising thing happening in this model. Namely, if we just, instead of diagonalizing the Hamiltonian on a ring, we diagonalize it on an open chain, then actually it turns out that the ground state is no longer unique, but instead there's a fourfold degenerate degeneracy. There's a fourfold degenerate ground state, and this degeneracy is actually due to some localized spin 1/2 degrees of freedom that reside at the edges of the chain. Right? And that's quite exciting because we started from an integer spin chain. So all the elementary excitations of this chain are actually, all the bulk excitations are of integer spin. However, the ground state has some fractionalized spin 1/2 degrees of freedom that are localized at these edges. And then this is now characterizing properties of these spin chains. And this is, in fact, also it's not a sort of a kind of theoretical ambiguity, but it's actually something that can also be measured in experiments. So, for example, there are certain materials that are in a good approximation described in terms of one-dimensional spin 1 chains. And if these systems are doped with non-magnetic impurities, then the NMR experiments actually show indications of half-integer spin excitations. So this is a quite interesting property. And I want to formalize this now a little bit, and this gives then rise to these symmetry-protected topological phases. Right? So let us now assume that we have some one-dimensional Hamiltonian and find the corresponding ground state to it. And we assume that both of them are symmetric under some symmetry transformation. So this could be just some arbitrary symmetry group. For concreteness, these could be just spin rotations. Recall that the Heisenberg chain, for example, has an SO3 symmetry, and these could be like these elements from the symmetry group could be spin rotations around different axes. So now we take the ground state wave function of our system, and we apply to it the symmetry operation, right? So for these spin rotations, we could maybe rotate every spin by a certain angle, right? And we just apply this globally to the entire system. Now, for our spin 1 chain, the representation on each side is just a simple kind of linear representation of the group. Right? So this is just the spin rotation in terms of integers. And the bulk, as I said before, is invariant under this representation. So if we had a system with periodic boundary conditions, the state wouldn't change at all. However, the boundaries can, in principle, transform in a different way. In particular, if there are degeneracies, the representation acting on the boundaries of a system can actually mix different degenerate states, and by this form a so-called projective representation. So the projective representation is something that's known to mathematicians for a long time, and projective representation is just the same as a simple kind of linear representation modulo some phase factor. Right? Just recall that if we have a simple sort of linear representation of a group, the multiplication of the elements of the representation, like UG times UH, is just the same as the representation of the product of those two group elements. For a projective representation, however, we actually find that there's some phase factor here that can appear like so that basically UG, like the representation of G times the representation of H, is just some phase factor times the representation of G times H. And in fact, we know that this is the case for example, for spin 1/2 degrees of freedom. And now, having introduced this concept of projective representations, one might ask a very general question, and this is a question that Isaac Schur asked himself more than 100 years ago. So let's say that you just take your favorite group and you write down two different projective representations. Right? So there are certain constraints of choosing these phase factors because you want to have a representation that fulfills associativity. So now you just chosen two sets of phase factors. And then you can ask, well, just by rephasing individual elements of this group, can you actually transform one projective, like the first projective representation that you found, to the second one? And it turns out that you can then group the different projective representations into different classes. And this is in he calls it the Schur multiplier, or in the modern language, these are kind of the second cohomology group. Right? So now we have just the classification of different projective representations. Right? So this is now, at the moment, just a purely mathematical statement. Right? And all the ingredients, we choose a group that we like. We just write down projective representation, which are just regular or linear representation modulo some phase factor, and then there's a way to classify these different representations.
Sorry.
Yes?
So what's the reason behind this fact that in bulk that those should be normal representation, I mean the ordinary representations, and on the boundary projective?
Right. So at this moment, I've just kind of I just assume that we have linear on-site representation in the bulk. If we don't have a linear on-site representation, if we have like an on-site projective representation, then this Liebstolz-Mattes theorem applies, and we would actually have a gapless state.
Okay.
But we want to have a gapped state, so I just assume that we have now a linear on-site representation.
Okay.
Right. So this is now the ingredient that we have linear on-site representation, and then we can have projective representations at the edge. And for projective representations, we actually know from mathematics that they are kind of classified in terms of the kind of second cohomology group. But now, this basically directly kind of generalizes to a classification of symmetry-protected topological phases. And the idea is now the following. You just write down your states. You just take a ground state, and the way how the symmetry transforms the how the symmetries act on the boundaries actually dictates us like what kind of symmetry, which kind of class the induced projective representation belongs to, and by this we can then just directly adapt the projective representations kind of scheme. A classification scheme to the classification of topological phases. So let me illustrate this in some more detail. So as I said, we just take whatever symmetry we might be interested in, or that we like, or that a system has, and then we can construct projective representations. And let's just start off with a very simple group. So we just take the group Zn, which is just the symmetry group of the star that we can rotate. So we know that if we just rotate the star n times, then we just go back to itself. So this is r to the power of n is the identity. But for our projective representation of Zn, that means if we just rotate the star n times, then it's e to the I some phase factor times the identity. Right? So now we have created a projective representation of the Zn. But what we can now just redefine our UR just by multiplying a phase factor e to the minus I phi over n times the original UR. But that would remove any phase that we could add. Right? So the upshot is that for Zn, no matter what kind of phase, like whatever phase we come up with, we can just remove it by adding another phase factor to this element of UR. And by this, we have shown that every element in this can be lifted to just a trivial representation. Right? So if we have just a simple Zn group, then there is only one class of symmetries. And if we just basically apply this kind of finding to physical systems, then we know if we have a simple kind of spin system with only a Zn symmetry, then we cannot have any symmetry-protected topological phases. There's only one trivial, one symmetric phase. So we just go to a slightly more complicated group, which is a group of Z2 cross Z2. Right? So this would be the symmetry group of some object like that. So basically, we can rotate it about two kind of orthogonal axes. Now, for each of those elements, like say for Rx and Rz, we can play the same game as here. So we can just, we know that Rx squared is equal to the identity, and also Rz squared is equal to the identity. So we can use it to fix basically the phase factors of Ux and Uz, right? So with this, basically we fixed now the phases of the two, or like the representations of the two generators of this group. But there's now another identity, namely Rx times Rz commute. So Rx times Rz is equal to Rz times Rx. But that actually allows us to have some other phase factor, namely that Ux and Uz is equal to some phase factor times Uz times Ux. And because of the fact that this is like an order 2 group, this phase can be either 0 or pi. And this phase factor can now no longer be gauged away because we already used our degree of freedom that we had to fix Rx squared and Rz squared to 1. So now, from this argument, we can actually see that there are actually, if we have a group Z2 cross Z2, then there are actually two inequivalent projective or two inequivalent representations. So it is either just a kind of linear representation, or it is a kind of non-trivial or projective representation. And they cannot be transformed into each other just by rephasing any operators. So that's now quite neat, because now we have found that there is this Z2 cross Z2 group. And if we have a physical system that has this Z2 cross Z2 group, then this Z2 cross Z2 symmetry, then we actually know that they are different topological, different symmetry protected topological phases that we can distinguish. Good.
Sorry.
Yes?
You said we already used the gauge figure we have, but by fixing R squared to 1.
Yes?
You need the same thing in the end.
Yes?
Fixing your R to 1.
Yes?
And how come we still have the degree of freedom here?
Oh, I mean, here the only kind of the identity that we have is that Rn is equal to the identity, and then we have this phase factor e to the I phi, which makes it a non-trivial representation. But this we can just gauge away. So here, that's why I said that whatever phase we choose here, we can just get rid of it. Now I'm taking this Z2 cross Z2 group, so we have now so we have now Rx and Rz. And now, just start over with this, I could say that, well, we actually know that Rx squared is equal to some phase factor times identity, and Rz squared is equal to e to the I phi z times identity. But I can now basically just use these 2 degrees of, I can just now basically choose my prefactor in such a way that Rx squared or Ux squared equal Uz squared equal to identity, so that the phase is trivial. Right? So now I fixed those guys. But then it leaves me the other identity, namely that because Rx and Rz commute, then I know that I could, like from the way that I've chosen my phases, there could be another non-trivial phase here. But now, since I already, so I just basically chose the phase of Ux and Uz, I cannot get rid of this one. So I cannot get rid of this one, but that would imply that I have now another non-trivial phase on either Ux squared or Uz squared. Does it make sense? In fact, yeah, and this is something that you can do for any group, and there are books on listing for rather complicated groups what kind of projective representations you can have and classifies them. But our main goal is now to kind of classify different phases of matter. In particular, we want to extract this information from our simulations, for example. Let's say that we have now a given Hamiltonian, and the first check is that we find that the ground state of the system is actually symmetric, right? So then we find that there's a unique ground state for our system, for an infinite system, and then we know we have a symmetric phase. But the question is like how to extract the these kind of representations. And in fact, the information about what kind of projective representations we have is directly encoded in the Schmidt decomposition once again. So let us now say that we have found the ground state for an infinite system. So we don't have any physical edges in the system, but then we can perform a Schmidt decomposition of the state into just by cutting it at a given bond, and giving us these Schmidt states, alpha left and alpha right, like exactly what we did before for motivating our MPS approach. But this is kind of giving us access to some sort of virtual edges in the system, and these are good enough to extract these projective representations. And it's actually as easy as the following. We just take our symmetry group, which is now so we just basically take the symmetry operation, which could be just a spin rotations or alike, and act with these guys just on our spin chain, like on the, actually this should be an R, right? So we just take the product of all those symmetry operations and act on those on the right-hand side of our, on the right Schmidt states, and form a representation of the symmetry group in terms of our right Schmidt states. Right? And this kind of tells us exactly how these Schmidt states transform under a symmetry. And for the Z2 cross Z2 group, which is actually a subgroup of the symmetry that we have in this Haldane phase, we can then just find the ground state and then obtain the representation Ux and Uz independently just by acting with the symmetries on these Schmidt states, and then calculate just the commutator of Ux and Uz. And this gives us exactly the phase factor that I was describing earlier on. And now we can take a Hamiltonian, for example, the one here. So we just take the Heisenberg Hamiltonian, which has this kind of Haldane phase ground state, and we add to it what we call a single ion anisotropy, like d times the sum of Sc squared. If this term is getting very large, then the ground state is simply the product state of Sc equals to 0 eigenstates. Right? So if I look only at this term, this is the exact ground state. And then we actually can calculate this, basically this topological invariant, which then tells us whether we are in the Haldane phase, where Ux and Uz anti-commute, or we are in this sort of large D phase, where Ux and Uz commute.
Sorry?
Yes?
Alphas, like, typically there are many different alphas, right? So this representation will have, it will be hugely reducible. Is that correct?
Yes. So this will be different blocks. So if you just are in the kind of non-trivial phase, there will be just kind of irreducible 2 times 2 blocks, and in the other phase there will be just one-dimensional representations.
So you, like, this invariant is not, it's not in alpha prime space, but rather in some irreducible block, in some irreducible 2 by 2 block.
But you don't need to know about this. Like, the idea is really that you just take the kind of large Schmidt values, like the ones that we used for constructing the MPS for the matrix product state, and then you actually have a large matrix. This could be a 100 times 100 or 1,000 times 1,000 matrix. Doesn't matter, but you just look at the whether these matrices commute or anti-commute.
Okay.
Mm-hmm. Good. Right. So this gives us now direct access to this kind of topological invariant.
Sorry.
Yes?
Why do you, on the representation, you only add on the left part of this?
No, as I said, this is a typo. This should be an R. I just act with the symmetry on the right-hand side. Good. But this kind of just directly relates to the matrix product state representation as we discussed before, right? Because when we choose this matrix product state in this canonical form, the Schmidt states directly relate to these indices of this matrix product state, and then we can actually write down a form how the matrix product state transforms under the symmetries. And particular, if we now take one matrix from our matrix product state, we act on those with a symmetry. So this can now be the spin rotation. We act on it on every physical index, right? So the operation goes as that we take our state and we just transform it by acting on every side with this symmetry operation. Then it transforms under this way. And these are now exactly the projective representation as they would act on these Schmidt states, because the way that the state, like for this canonical form, the way that we've chosen these matrices is in such a way that these correspond exactly to these Schmidt values. They can also differ by some overall phase factor that I haven't really discussed about. So, and this kind of gives us now a very direct way how we can extract the this kind of topological invariant from a matrix product state simulation. So in particular, we just construct this object, which is the same as what we looked at before, namely this transfer matrix for which we found that the dominant eigenvector is just the identity. But now instead of just having a transfer matrix, we just sandwich here the symmetry operation, sigma, and we just look at the dominant eigenvector of this guy. And this actually gives us directly the representation of sigma or of like any symmetry operation. And the way that we can see this from the previous is the following. So from what I said before is that what we want to obtain is the representation of the symmetry operation in terms of our Schmidt states. So now, and also in the earlier lecture this morning, I said that, well, if we have a state in the canonical form, we keep this left index fixed. We just multiply all the matrices to the right of this index. Then we get the Schmidt states, right? So what I'm plotting here, the expression that I illustrate here is exactly, this is now, say, the Schmidt state alpha right. This is now the symmetry operation acting on all physical spins. And this is now, say, alpha, the Schmidt state alpha prime. So this is exactly the expression that we had before. If I act on these guys with the matrix product state, then I just get exactly this representation that I'm interested in. So where I'm here acting with the symmetry operation just on the upper Schmidt states. But this guy is now exactly just the transfer matrix for which we know by definition that the dominant eigenvector is the identity. And here we find that this is now just the dominant eigenvector of this mixed transfer matrix. So from this we can directly see that the representation is just directly given by the dominant eigenvector of this sort of mixed or generalized transfer matrix. So even though maybe conceptually not so easy to see, in practice this is like quite straightforward. So if you're having some infinite system TBD or DMRG code, you take the ground state that pops out, so you just get the matrices, and from these matrices you can directly construct this mixed transfer matrix, which is just multiplying the matrices together with the symmetry operation, and then you just diagonalize this matrix. And from the largest eigenvector of this matrix, you can then directly read off the topological invariant. And another way to learn from these simulations about what kind of topological phase you're in is, and this is now related to the question where you have these irreducible blocks. If you have projective representation, then you know that the smallest irreducible block has to have a dimension 2, so it's always an even dimensional representation. So then you can look at the entanglement spectrum, so which means that you just look at the the entanglement spectrum is just the logarithm of the Schmidt values squared. So you find that all the Schmidt values actually come in pairs in the Haldane phase, while they just can have any kind of multiplicity in a trivial phase. So these are basically what I'm pointing out here is that if you are performing these matrix product state simulations, as we discussed in the first lecture, you can just read off the information about one-dimensional symmetry-protected topological phases basically right away by looking at the entanglement spectrum. And if you want to just get some more information about it, you can just look at the eigenvector, the dominant eigenvector of the transfer matrix. Good. Are there questions about this part? Good or not good? I don't know. So, yes?
Here you have 6 eigenvalues, the lowest eigen, 6 entangled.
Why 6? I don't.
Entanglement spectrum, right?
This is entanglement spectrum, yes?
Yeah, you have 6 lowest values, right?
Where do you read off the number 6 from? You mean like these ones?
No, the lowest ones. It doesn't just give you the degeneracy or...
I mean, here I'm plotting the entanglement spectrum as function of the of D, like of this parameter D, and at roughly D equals to 1, there's a phase transition from this Haldane phase to this large D phase.
The degeneracy of your entanglement spectrum gives you the edge degree of freedom, right?
Yes. Exactly. So this would be this is a degeneracy of one edge, and if you were to consider 2 edges, like in a finite system, then you would find the square of this degeneracy. So you would find a degeneracy of 4. Good. So as promised, I mean, I wanted to discuss, just give you an overview of a few different topological invariants, and this was for so-called interacting symmetry-protected topological phases. And in the second part, I want to discuss some topological invariants for so-called intrinsic topologically ordered phases. Right? So I think in the lecture by Alex Alland, you already heard about the toric code model, which is an example of a model that exhibits this topological order. And another prominent example is the so-called fractional quantum Hall effect. Right? So if you look at the fractional quantum Hall effects that occur at fractional filling factors, the system forms the so-called fractional quantum Hall effect, which has this kind of topological order that I want to talk about. And the example, which I, again, not going to discuss in a lot of detail, but the DMRG techniques that we introduced in the first part, which are mainly, which are intrinsically kind of one-dimensional model, one-dimensional methods, can be applied to these systems in a rather neat way. In particular, when we consider fractional quantum Hall systems not in a kind of really two-dimensional limit, but instead we put it on the surface of a cylinder of a certain finite circumference, then we can effectively map it to a one-dimensional system. And the basic idea is that we take the system on a cylinder and choose the Landau gauge. And in the Landau gauge, we find that the single particle orbitals are localized in the y direction, and they're extended along the x direction. And this gives us now some effective one-dimensional representation of the system. Right? So we have now our two-dimensional continuum model, and if we just restrict it on the cylinder and choose, say, just only the lowest Landau level, then we actually have this nice one-dimensional representation of the system. And from this one-dimensional system, like having this one-dimensional representation of our problem, we can then use the techniques that we introduced before. Maybe we can use then a matrix product state representation for describing the fractional quantum Hall states on a cylinder. And what we are then looking at is we say that, well, we define a certain filling factor, so for example, 1/3 of the lowest Landau level, and then we just take into account maybe some Coulomb interaction. So the Coulomb interaction, which is just 1/r in real space, transforms to some different expression where we go to this orbital basis. But this is something that can be easily done. And then we have a Hamiltonian acting on this one-dimensional system. And the price we have to pay is that instead of having rather short-range interactions, the interactions get longer range in this one-dimensional representation. So there's a number of things that I swept under the rug, but the upshot is really that we have a two-dimensional system that exhibits interesting topological properties, and we can, in the limit of putting it, when we put it on a cylinder, we can map it to a one-dimensional Hamiltonian, which we can then treat using our matrix product state techniques. And from that representation, we can then extract topological invariants again. And let me just very briefly just point out what these topological invariants are that we are interested in. So the characterizing property of these topologically ordered systems is the existence of some rather exotic quasi-particle excitations, namely so-called anionic excitations. Right? So these anionic excitations are particles or point-like objects that when we're exchanging them, they can actually have phase factors that are different from just being simple bosons or fermions. And, there's some scheme that we can now use. Like basically, we can just look at what kind of anionic excitations we have on top of a given ground state, and this gives us a way to classify different topologically ordered phases. And that by itself is, of course, not very easy because we would have to create these excitations. But in fact, there are some implications. So just having or knowing that there are these excitations, we actually can derive from this the so-called topological degeneracy. Namely, if we take the ground state, find it on a sphere or like on an infinite plane, we would find a unique ground state because the ground state would not break the symmetry. But if instead of putting it on a sphere, we're putting it on a different topology, for example, on a torus, then the ground state would have a degeneracy. And the degeneracy would correspond actually to the number of different types of anyons that we have in a given theory. Right? So this at a rather superficial level gives us this idea of a topological invariant. We just take our fractional quantum Hall system, put it on a cylinder, and just from the degeneracy, we can now tell how many different types of anyons we have, and this gives us some idea what kind of phase we have. Right? If we have, for example, a so-called Loveland type of topological order, then we know that the degeneracy should be 3 because there are 3 different types of anyons. And another way to characterize these phases is again in terms of their entanglement properties. And this is a so-called topological entanglement entropy. And similar to what we discussed at the very beginning today, there's this area law in 2D. As I pointed out, hasn't been proven for 2D, but for many of the interesting systems, we actually find it. So which means that the entanglement entropy of a disk, or if you look at how the degrees of freedom within a disk are entangled with the rest of a system, scales proportionally to the area, which means it's just the length of the cut, right? So it's just a two-dimensional system, and where the area would just be this one-dimensional line here. So the dominant contribution would be just alpha times L, but then we have have some additive corrections, and this is specific for topologically ordered systems. So we would actually find that there's a constant contribution here, and this constant contribution is now again a sort of topological invariant for these systems. In particular, for some simpler type of topological order, namely where the anyons are so-called abelian anyons, then this topological entanglement would just be the logarithm of the total number of the anyons. Good. So this gives us now some kind of quantities that we can look at for characterizing different types of topological order. And the second one is now quite convenient for us to calculate. So as I said, with this DMRG technique, we can put the our fractional quantum Hall system, for example, on a cylinder, and now perform calculations for different circumferences of a cylinder. And in this cylinder geometry, for this cylinder geometry, we actually have L is now just the length of our cut if we look for a bipartition between the left half and the right half. And we can now just calculate the entanglement entropy, which we just get directly from the Schmidt values that we have access to. And then we can just plot the entanglement entropy as function of L, like of a circumference, and we find that the dominant contribution is just this linear slope, and this we can just extrapolate and see where it hits the y-axis, and from this we can then read off this value of gamma, like this topological entanglement, and for this kind of mu equals to 1/3 topological state, we expect this as at the logarithm of square root of 3, and indeed this is where it very quickly converges to. So here we can then just read off topological invariants directly for the states. And that works extremely well for certain cases, as the one here, but it also, if we have other cases, like for example for the 7/3 filling, we theoretically expect it to converge to the same value, but we see here that the convergence is much slower in the circumference, so we would have to go to really large circumferences that are far beyond what we can reach to tell what the actual value is.
Can you please comment on what circumference we're talking about inside, like actual site?
Well, it's inside. So here we measure the circumference rather in magnetic length, because it's a continuous. So here we have a continuous system. So it's a continuous quantum Hall system, and the characteristic length is in terms of magnetic length. And for the larger systems that we looked at here have 30 magnetic length in the circumference. Good. So this is one way that we can address these systems, but in fact, using some slightly more involved tricks, we can also extract other quantities from it, including the topological spin of the anionic excitations, and also the central charge of the boundary theory and Hall viscosity. So this is for a continuous system on fractional quantum Hall. But one thing, and this is like one of the motivations that I started from in the beginning, we can also look at two-dimensional lattice systems, right? And as a motivation, I talked about this kind of Haldane model, and I said that, well, one of the interesting questions would be if we just partially fill the lowest band, then we have clearly without interactions a metallic state, and if we turn on interactions, then there can be interesting transitions from this metallic state into some topologically ordered states. And in particular, it had been argued that for the for these kind of systems, that if the interactions are strong enough, meaning if they are strong enough compared to the flatness of this lowest band, then there could be some fractional quantum Hall physics emerging from this lattice model. And again, we can choose, or we can use these matrix product states for simulating these two-dimensional systems. And the trick is now the following, namely we put as we did in the fraction quantum Hall case, we put this two-dimensional system on a cylinder of a certain circumference, and then we enumerate the sites in some one-dimensional manner, as done here, with this kind of snake counting the number of sites. And then the interactions, which are local in this two-dimensional way, so here maybe only nearest neighbors couple, this translates into a longer range interaction of this one-dimensional representation. Right? Just to repeat this, so for this simple case of this square lattice, we could enumerate the sites as 1, 2, 3, 4, 5, 6, 7, and so on. The original model on the square lattice is only coupling nearest neighbors, but if we translate it to this one-dimensional labeling of our sites, then we see that now site 1 and site 5 are coupled. And what we from this get is that we can now simulate the two-dimensional physics at the cost of having these long-range interactions. And that's actually quite bad, because as I pointed out, if we assume that there's this area law for states in 2D, then we find that the entanglement entropy will grow proportionally to L, and that generically will mean that the number of states that we need to keep for a given precision will actually increase exponentially with the circumference L. So these calculations become rather expensive when we're going to go to circumferences larger than a certain number. But for interesting physical systems, like these kind of fractional Chern insulators, for example, we can actually go up to system sizes up to 12 sites. And by this, we can reach then states that are, or systems that are significantly larger than what can be achieved using, for example, exact diagonalization. So, and once this is implemented, we can then look for exactly the same kind of topological invariance as before. For example, we can look at the topological entanglement entropy of the system and extract again the topological entanglement entropy that we would expect for these kind of Laughlin type of states, which we can take as a hint that the system actually realizes fractional quantum Hall physics. And other experiments that we can do on this is we can do charge pumping. This is this Laughlin's charge pump by adiabatically inserting a flux to the system. Then we see that it takes 3 flux quanta to pump 1 quantum of charge from the one side of a cylinder to the other. And this is actually also something that we will look at in the hands-on session this afternoon. And then we can also look at the edge states in terms of the entanglement spectrum, which show some characteristic properties of chiral states predicted by some effective edge theory. I realize that this is just a very quick overview, but I think it might be useful that you see what are the possibilities that we have. Joel, I think I probably should wrap up rather soon, right? Or
yeah, I think you have 10 minutes if you want them, including questions.
Okay. Yeah, let me then just maybe very briefly just show a few slides about the dynamical part, and then we can jump right into the question part. So once we have the ground state properties of a system, we can use the same techniques to also learn about the dynamics of a system. And this might be quite useful also for people who are more interested in experimental signatures of these phases, because topological entanglement entropy and the like are not easy to measure. And just as a sort of motivation, if we look at dynamical response function, it tells us a lot about the excitations. And a very nice example is a one-dimensional spin chain where the excitations, the elementary excitations are spinons, giving us some kind of some continuum excitations. And these can be, on the one hand, calculated theoretically on the right-hand side, but also measured in the neutron scattering experiment shown on the left-hand side. And this kind of provide very useful insights into into the nature of these states. And of course, it would be interesting to understand this not only for simple one-dimensional systems, but also for higher dimensional systems. For example, for two-dimensional systems. And the DMRG techniques that I've demonstrated so far can be directly used to calculate these dynamical structure factors. So in short, the idea is that we first find the ground state of a given Hamiltonian, and then we hit this ground state with some operator, like we just perturb a local perturbation, which we can then time evolve. And from the Fourier transform of the dynamical correlations, we then directly obtain the structure factor. And well, if we do this, then we can just calculate, for example, for a two-dimensional, in this case, it's a specific model, specific kind of frustrated model that is known to have some interesting sort of topological properties. We can just calculate the dynamical spin structure factor and compare it to experiments. Well, let me then conclude here with this, so that I hope that I took more time to actually to explain some of the basics, including the entanglement properties, matrix product states, and gave some algorithms that we can use for simulating these systems. I gave a glimpse at some ideas how from these simulations we can extract topological invariants for interacting systems. And I just showed a slide or two on the fact that we can also extract the dynamical properties using these techniques. And let me also at this point advertise that we put online some kind of Python toolbox for doing these kind of simulations. This is mainly from Johannes Hauschild, who is a PhD student in my group. And there are also some accompanying lecture notes that explain in much more detail what I went through in the first part of this lecture. So you can read these details here. Okay, then thank you for your attention. Well, I mean, this is a good question. So if I want to express them, so I think the statements you're referring to is that these chiral states are very difficult to express in terms of two-dimensional tensor product states. Now, here we are not even trying to express them exactly in the thermodynamic limit. Right? So our idea is just we put them on a cylinder, and we already know that there will be an exponential growth of the bond dimension as we go to larger and larger cylinders. Right? So we are not competing with this statement of saying that, oh yeah, we need a large bond dimension for expressing them in two-dimensional tensor networks, because we already know that this will be the case for MPS. It's just by pushing it in terms of the numerics that we can still say something useful about it.